Welcome. Exam review. So the first module in the course was dimensional analysis. So we did dimensional analysis review and we did pi theorem. So the lesson one was dimensional analysis review, and in this lesson we learned about the primary dimensions. So the primary dimensions that you need to know is length, mass, time, and temperature. Uh, There is also electric current and the amount of light, and there is also the amount of matter like moles. So you as a civil and environmental engineer, the main primary dimensions that you will see in the equations that you will typically encounter in fluid mechanics, in thermodynamics, in aquatic chemistry, in these types of equations that we generally deal with would be mainly related to length, mass, time, temperature, and the amount of matter. So yeah, so expect to get these in the exam, like something related to this primarily dimension. Uh, I prepared like from this non-primarily dimension are formed by combination of this seven primarily dimension, and I provided like if you go here, you can print this, for example, with you as a PDF or whatever. Yeah, so you can, I provided for you some of the, so this is length, time, and mass. These are primarily dimension. Like the units of this could be anything. It could be like the SI unit, for example, could be is meter, for time is second, for mass is kilogram. The dimensions that we generally use is LTM. Uh, and this is some like comments. So you can see like density, for example. So this is a non the equation for it here and the unit and so on and so forth. So you can, these are basically like if you have a table like this, that should help you a lot through the exam. So I highly recommend that you will like have it as a PDF or something with you, yeah, or any similar tables that you have, yeah. So like you have, and make sure you understand all these things because as an engineer, these are things that we you learn it in engineering mechanics, statics and dynamics, and things that you learn it in fluid mechanics, and these are very basic general knowledge that any engineer should have. Yeah, all I just put here the main ones. Yeah, the main things, the general knowledge that any engineer should have, civil and environmental engineer should have. Yeah. Okay. So this pay attention to this and like we did some practice. So for example, like this is something you've never seen before. I mean, it's called like intrinsic permeability, whatever that is. So, and I'm asking you what is dimensions of this or and how can you do this? Like you have an equation for it. So you have an equation like K, hydraulic conductivity, is equal to this intrinsic permeability or permeability times specific weight divided by viscosity or dynamic viscosity. Uh, Again, maybe I don't know what is the unit of this guy or the dimension of this guy. We have an equation for it. So for this guy, we have an equation Q. So I know this. This is like Q that is volume per time. Yeah. And I know head like that's like length, x like distance, that's x, so that's like will cancel out together. Here this is area, it has like the, so this is an area, so this guy will be like L square, this guy is volume over time, so that's like L cube over time. So then what would be the unit of this guy? So like this will go away with this, so the unit of this guy will be like length over time. So now I know the unit of this guy. So now I know that this is length over time. Uh, Specific weight, like this is weight per unit volume. So I know weight, like weight is like mg and volume like that. So you can, know this, yeah. Or I can check it like in the table. Like I can go to this table and like check what is dimension of this guy. Similarly for viscosity, if you don't remember the dimension of viscosity, like you just go to this table and check it here. So here you just like go here and like, so this is the viscosity, that's like ml negative 1t minus 1, yeah. So you check it here. So you see here like viscosity ml minus 1 t minus 1, yeah. And for this one, like specific weight, you can either drive it. So like I know like m, so that's m like g, that's like acceleration. So acceleration, that's like length over t minus 2, and volume, that is like L cube, yeah. So that will, so this will give me m L t square. So that would be like, yeah, see, that's, you can drive it, yeah, for this guy here. Yeah, this is what we did. And then like you substitute here and then you get the dimension of this guy as L squared. So you should be able to do like this dimensional analysis to infer, for example, like the dimension of something you don't know, or to ensure that you have dimensional homogeneity. So dimensional analysis, like here, for example, I'm telling you what is dimensional, verifies the dimensional homogeneity of Bernoulli equation. So here I know that the dimension of this guy should be the same as the dimension of this guy, should be the same as the dimension of this guy, should be the same as the dimension of this guy. So for example, like g over z. So g, remember this is like acceleration, so that's L t minus 2, and this is z. So what is z? That's like L. So the dimension of this guy, that should be like L square t minus 2. Yeah, see, that's what I got here. Yeah. Similarly, if I did like velocity, so what is velocity? Velocity is like is L over t, and then like squared. So here I will get like L squared over t minus 2. Yeah. So for this one, I got like the same as this guy. Similarly here, pressure over rho, so you can pressure like that's force over area, rho that's like mass over volume. If you did this, you will end up with something like this. Yeah. And so what is the, here again, what is the dimension of this constant? It is the same. It should be the same as this guy. It should be the same as this guy. It should be the same as this guy, which is like L squared over 2. So make sure not to make these mistakes. You'll have also this in the exam. I will give you something like this and I will tell you like to ensure like it has dimensional homogeneity. Yeah. Okay, so we learned this. Another thing we learned is the pi theorem. So the pi theorem, for the pi theorem, dimension analysis scales results between geometric scaled model and full scaled prototype. So you have like geometric, like a scale, a physical model and your prototype, and to be able to make inference from your physical model, like in the lab or in the field or whatever, to your prototype, uh, you should have at least geometric similarity. So the model must be the same shape as the prototype, scaled by constant factor. And you have kinematic similarities. The velocity field of the model proportional to the velocity field of the prototype. And in order to ensure uh, full like similarity, you need also to have dynamic similarity. So here, this has to do with the length, uh, uh, and here this has to do with like the velocity field. So this has to do something with velocity, like time, and here all forces in the model, like internal, gravitational, viscous forces, scale up by constant factor to the corresponding force in the prototype. So here this has to do with forces like with mass. Yeah. So here you need to ensure L, for example. Here you need to ensure T, and here you need to ensure like M, mass. Yeah. So like something related to length, something related to time, and something here related to mass. Yeah. Because remember, like force, it's like mass time acceleration. Yeah. Yeah. velocity is like length over time. And like the shape, that's like L square or like volume, yeah, something like this, yeah. Okay, so we learned it like for the dimensional analysis, you can be generating non-dimensional parameter to design experiment and report results. We know that this is something very useful. Like if I want to make an experiment and report like the result, if I want to reduce the number of my independent variables, so what I can do, I can compile like this independent variable with some dimension less parameters, yeah, with some dimensionless parameters. So here, for example, like I give you this drag force. So drag force, that's something that you will encounter in many engineering application across fields, and you can make like see like okay, drag force, like the drag force is could be like a function of the diameter of my object, yeah. So it could be a function of like the diameter of my object, like here, like the diameter like of this guy. It could be a function of like a velocity. It could be a function of the fluid density and viscosity. Yeah. So the velocity, velocity of the flow fields, uh, density of my fluid, and the viscosity of my fluid. So my fluid here, for example, with this wind uh, miles, that would be air. The fluid here, that would be water, for example. Here it will be air. Here will be water, things like that. So I can have, okay, I think it's like drag force is a function of diameter, like something that has to do with length. Velocity, something that has to do with kinematic similarity. And density and viscosity, that's something that has to do with dynamic and dynamics similarity. Yeah. So that's a function, but I don't know whether this is like inverse correlation, directly correlation. I don't know whether this is linear or non-linear. Uh, I don't know all this, but with dimensional analysis, I could come up with a better understanding, like whether this is like an inverse or uh, correlation or direct correlation, whether it's linear or non-linear. So here, there we talked about like you have like you use the pi theory, and like in that case, like if you have five variables, then so n will be equal to 5, then you will have two dimensionless parameters. Yeah, that's usually the rule. If you have six variables, then you will have like three dimensionless parameter, like 3 terms. If you have like seven variables, then you will have uh, 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 four dimensionless parameter if your system is mainly controlled by like length, mass, and time. Yeah. So you choose the pertinent variable. So here we know that these are the pertinent variables, the important variable. You choose the repeating variable to represent all dimensions, but not to include dependent variables. So the repeating variable, it should not include this. And the repeating variable, uh, that should also, you should choose them to include like length, time, and mass. So you should include something that represent length. Obviously, that would be the diameter, for example. You should kinematic or time something that's time dependent, and that would be like velocity. Yeah. And dynamic, something that's like mass dependent, and that would be, for example, the row. And in a minute, like I will show you like why this is called like the repeating variables. Yeah, so you choose like your repeating variables. So here, this is like your quantities. This is the simple. This is the dimensions. So diameter, velocity, force, density, viscosity. And then you find the number of pi terms. And again, I told you the number of pi terms, that would be uh, 5 minus your m, like your repeating variable, so that would be 2. Okay. Again, your repeating variable should include MLT. If you have other primary dimensions, then your repeating variable should include them. But in that case, we only have MLT. Like everything here is MLT. Yeah. If there's other things, uh, amount of matter, what are like temperature, whatever, then that should be like presented in your here like that. So here, for example, that would be MLT and like temperature if you have temperature. Okay. But anyway, and then you will put here like your first pi term, you will have like your three repeating variable plus the plus one of the remaining variable, which is in that case your independent variable like the drag force. And then your second pi term, you have your repeating variable plus the other pi, like the other variable, which is in that case would be viscosity. And then you just follow this step. I'm not gonna go through like this step. Basically, like you substitute the dimensions here. You know, like that this pi term is dimensionless. So what does this mean? Means like m is equal to 0, L is equal to 0, T is equal to 0. That's how you make it dimensionless, because that's exactly what I want to do. I want to make this dimensionless. Then you collect all the terms and you solve for m, you solve for L, you solve for T. Basically, you find the value of A and the value of B and the value of C that will also make this dimensionless. Because remember, dimensionless homogeneity means what? If the left hand side is dimensionless, the right hand side should also be dimensionless. So I find the value of A, B, and C that makes the right hand side dimensionless. So you do this, and then like you substitute here, and then you repeat the same here, like you substitute here. So that's like your repeating variables, that's your dependent variable. And after you do this, now all this right hand side is dimensionless, similar to the left hand side. So this is dimensionless, this is dimensionless. Here again, like this is dimensionless, this is dimensionless. Now I could I've seen here something that I can recognize. So this is like mu over rho VD. I mean, if I just flip this, I will get the real number. So I can just flip it because again, this is dimensionless. If I flipped it, it's still dimensionless. So like if I brought like this up and brought this down, that is still dimensionless. So now I reorganize it like my pi 2. And here for my pi 1, I recognize this is something that I know also the drag coefficient. So now I have a relationship between like my pi 1 as a function of pi 2. That's like the drag coefficient as a function of a real number. And that's basically how I can make and report like this experiment. So like if I want to make this experiment, I just like drag coefficient as a function of real number, and that will capture all the variation in diameter, in velocity, in the density, if I want to change my fluid, and the viscosity if I want to change the viscosity of my fluid. So again, these are basic concepts that you need to understand. If you need more details, you can go back to the original video. But once I am, I have like these two non-dimensional parameter, like so what? So what? Like actually, if when similarity is achieved, we can predict the prototype performance from the model performance, as is basically like what pi theorem is about. So I have like pi 1 is a function of pi 2, pi 3, whatever number of pi. Like in the previous example, pi 1 was just a function of pi 2. I didn't have like any of them. But if yeah, uh, my pi like 2, for example, like the red, like which in that case, in that particular example would be the real number, yeah. In my model and prototype are like this is dimensionless and this dimensional, I have like a similarity is achieved. If these two are equal, yeah, for any number of pi, then the pi 1 model and pi 1 like my dependent variables, they will be equal. So basically, in other words, if the dependent independent term between model and prototype are identical, then the dependent term will also be identical. And then I could make inference. Whatever I learn from my physical model, I can scale it back to the prototype. Yeah. So that is, I think, all for this lesson. If you need more details, you can check, go back to the recordings or go back to the slides of the original lesson. Okay, see you in next lesson. See you next exam review.